It's my pleasure to invite our next speaker, Michael.
Hello, everybody. I'm Mike Wilde. I'm with Argonne National Lab, University of Chicago, and more recently with a small startup in Chicago called Parallel Works. Our talk is actually representing what a large team of people has done over about a decade and a half to automate workflow-level coordination of applications. So whereas the other talks in this session were really focusing inwards on how to create HPC apps, what we're talking about here is how to coordinate their execution on very diverse hardware. So what we're talking about here is work done in the National Science Foundation and Department of Energy research communities. We haven't really focused very much on the oil and gas community, and one of the goals we have here is to give you a kind of a quick whirlwind tour of what we've been doing at the workflow, composition, and coordination level, and look for potential collaborators. If these are the kind of problems that resonate with some aspects of what you and your communities do, we'd love to work with you. So this is the kind of environment that we focus on. Users typically run somewhere in a large global international grid of supercomputers and cloud grid type resources, have a wide diversity of applications across a wide diversity of sciences, and want to coordinate workflow campaigns of those applications on these kinds of diverse parallel resources. So we're now literally in our fourth generation of attacking the problem of how to program at this scale. And the reason we feel it's important is because our observation of scientists in these communities show that a lot of people know their science really well, they know their app really well, but as soon as they start scaling that up and running tens of thousands of instances of it across diverse resources, they're really bottlenecked. And so these tools try to attack that bottleneck. So we started off with sort of a declarative data concept called virtual data language way back at the beginning of 2001. And this sort of taught us how to encapsulate code so that you could kind of capture the recipes by which data is derived in big scientific collaborations. We moved to a language-based approach mid-decade with the Swift language. And Swift was basically a parallel data flow language for this type of coordination. In 2008, 2009, we were funded under DOE XStack program to try to apply this language to the problems of programming the kinds of exascale machines that Lori talked about this morning. And indeed, the kinds of applications that she showed are exactly the kinds that our community deals with. And so that resulted in a very high performance version of this tool that not only did coordination of apps, but went in memory and also could do workflow level coordination inside a large app. And then finally, we've Pythonized this, and that's kind of the exciting message of the story. So what we found in developing all these models is that encapsulation is key. In other words, when you're trying to automate the parallelization and the distribution of these applications across grids and supercomputers and clouds, you need to know what's going in and what's coming out of every invocation of an app. So in other words, we take messy applications that typically have command line, config file kinds of interfaces, and we give them a very clean functional interface. And that allows the languages to be functional and implicitly parallel. And so when you look at like this kind of geospatial analysis application where you have a large data set, you may have to run several applications on that data set at a time, and you go through a pipeline of processing. We allow you to specify this in Swift. So you're looking here at code of the two Swift implementations of this kind of programming model. So it looks kind of like a simple functional program, but what's magical here is that everything that doesn't have a data dependency runs in parallel. So in other words, every object in the language is really what we call a future, coming from the Lisp parallelization community. And these data sets in the original version of Swift represented not what's in memory typically, but more commonly what's on your file system. And so we had mapping techniques to map file systems to arrays, and then everything is automatically parallelized. So for example here, all the two loops, every element of the first two loops runs in parallel, the workflow programmer didn't have to say anything to make that happen. It's implicitly parallel. And then as you go down the pipeline, anything that can run when a data object is ready runs as long as there's resources available. And that same kind of technique scales all the way up to Blue Waters, where the Polar Geospatial Center has used Swift to parallelize the execution of these large-scale models of the Arctic with extremely high resolution from government intelligence satellites down to the resolution of about, I think it's 1 pixel per 2 meters. So this kind of functional composition then leads itself to these deeply nested loops. And this is where we started getting then use Swift-T to express its massive parallelism. And the same kind of parallelism can then be used in memory. So for example, if you have an application like LAMMPS for doing molecular dynamics, LAMMPS has an excellent API to call subcommunicators, and you can basically, instead of running LAMMPS as a command line app at ensemble scales of tens to thousands of applications, can literally call it from Swift-T directly with a subcommunicator in memory. And it's also really good at large-scale image processing pipelines. If you have a diversity of tools that need to be stitched together, instead of writing kind of a messy bunch of bash or shell scripts, you can now have a very clean functional definition of the top level. So this workflow graph is then cleanly specified in a simple Dataflow kinds of program. And then each of these functions can either be representing an app, could represent an in-memory function, or could represent itself another mid-level function written in Swift itself. And then more recently, we sort of attacked what we felt was like the #1 barrier to really broad adoption of this programming model, and that is Swift was a really excellent experiment in how to make this kind of programming highly productive, but it was a new language. And so by taking that same programming model and moving it to Python, we're really kind of opening it up to sort of like take down the #1 barrier of I don't want to learn a new language for doing this. And so if you go to the parselproject.org site, you can actually go and try this, and it's runnable from notebooks and things like that. So in Python, we leverage the notion of a decorator to basically intercept function calls that are part of the Dataflow backbone. So unlike Swift, where in Swift everything was a future, every data object was a future, everything was parallelized, in Parsl, you use a decorator to declare just the parallel portions of your program, and then that internally uses futures that you then wait on at key points in the program. And as these apps run, they basically build a Dataflow graph, and you get the same kind of performance and capabilities and expressivity that you had in Swift, but now you're doing it in the comfortable language that you know and love. Okay? So Parsl has rapidly taken off, and not only its adoption rate is much higher, its participation rate from the community is much better, but it's also very quickly caught up with Swift in terms of what you can say in Parsl and the sophistication of its runtime language. So we'd love to talk with you offline about these kinds of benefits. It's kind of beautiful to be able to sit in Jupyter and then kick off massive scale supercomputing from a Jupyter notebook, to be able to sort of get logs that can show you what you've done very clearly in your workflow and audit your results with your colleagues. And then especially to scale it across very, very large and diverse resources. So Parsl has adopted the Swift frameworks for executors across diverse hardware. It actually has 3 classes of executors, and it kind of, unlike Swift, which kind of jumbled a few layers together, it cleanly separates the framework of pilot job execution to manage large-scale resources from the actual cluster-specific scheduler issues that you need to actually set the framework up or to dynamically launch the framework. So we have a high-throughput executor, a low-latency executor, and an extreme scale executor that all target different design points of the large-scale workflow space. I'm not going to go into too much detail on performance. This is from a paper that was recently submitted to HPDC 19, and these results will be published in archive.org real shortly. But the takeaway here is simply that one of the key challenges of a workflow language at these kind of scales is kind of its task rate. And with the 3 executors in Parsl, we've really gotten to be not quite as fast as the extreme scale Swift, which actually can do 100 microsecond tasks at like 1.5 billion tasks per second on 500,000 cores of Blue Waters, for example. But this clearly crosses the barrier in terms of number of cores supported, number of tasks per second, and things like that in pure Python, which is kind of a result that we were really excited about. And similarly, the scalability and latency is very, very favorable.
Get some reaction out of these.
The community, as I mentioned, talks to a really diverse set of disciplines. And one of the things we've done is attempted now to provide commercial support for this model. So I've actually taken leave from my team at Argonne and UChicago to join a small startup called Parallel Works, which is now taking these programming models, linking them with a pretty popular workflow user interface from the Galaxy project, and putting these all together into a nice approach to giving you hybrid HPC cloud access, for in a way that can directly encapsulate these things for end users. So one of the beauties of the programming model is with its regularity, we were able to easily integrate optimizers like Dakota or GenOpt from the national laboratories into a workflow framework. And when we talk about this, within and around kind of model, the beauty here is that the workflow can sit above the optimizer. You can run many optimization strategies and do a big optimization exploration in parallel, and each optimizer then can run its generations of test cases in parallel, all using the same uniform programming model. So in collaboration with INDYCAR and R Systems, R Systems being a cloud bare metal provider, Brian Cusick here was gracious enough to sponsor this project and can talk to you about some of the details of racing here. We're doing aerodynamic studies and supporting aerodynamic studies done by Tino Belli of INDYCAR to basically redesign the aerodynamics and sort of make racing more competitive and interesting. And so this design space inside Parallel Works allows you to sort of navigate through the results of a large parallel study, drill down into scored results. And what you're seeing here is aerodynamic studies of overtaking, doing basically a optimization sweep exploring different radii and angles of a leading and approaching car. Okay. Similarly, it's a great platform for doing hybrid computation, as I mentioned, making it very easy to stitch together HPC resources and cloud resources together. And so the same kind of design spaces are available. So I just wanted to give you sort of a taste of those capabilities, and be glad to take questions, and even more glad to talk to you offline about collaborating either with the open source teams that are developing this under NSF and DOE funding, or Parallel Works, which is looking for commercial opportunities to make these easier to use for a much broader community. So thanks very much. Yeah. Hi.
Thanks. So as an MPI programmer, I'm used to having a lot of control over the system. Mm-hmm. Where does this tool sit on that kind of assumption?
That's a great question. What we try to do is really have a separation of concern. So with trying for this holy grail of implicitly parallel functional programming, it really fits well at the high levels. It doesn't fit so well as you get closer and closer to the hardware, closer to the libraries and things like that. Swift-T kind of falls across those layers. Swift-T itself is implemented in MPI, okay? So what it's meant to do is to kind of program the upper levels of a large MPI app when you're using it in its kind of in-memory mode. And the vision there was that as we look toward exascale systems, what we were trying to do is to sort of capitalize on this idea that one set of problems are going to be the people who really take the apps and make the apps, you know, more performant portable. What we're trying to do is to coordinate the higher levels, which are really more suitable to the place where you're willing to give up control, because you're not dealing in micro or nanoseconds, you're dealing in milliseconds to days of, you know, large-scale execution. So we have the control in some of the models, and it's certainly in Parsl, you have total control because we've given up a little bit of portability, a little bit of the implicit parallel productivity for the control. So in Python, you can do anything you want in Python as long as you then try to leverage the framework in its prescribed manner. So. Hi.
Thank you. So you mentioned that the Parsl actually integrates with Jupyter with seamless workflow management. Could you elaborate more on that?
I'm sorry, I couldn't make out the beginning of your question.
So you mentioned the Parsl is integrated with Jupyter, right?
Oh, yes, yes.
Could you just comment a little bit more on that, elaborate a little bit more details
Yeah,
on
so
that?
the Parsl integration in Jupyter is really pretty simple. I mean, it runs in Jupyter exactly as you would run kind of normally. But what you can do is you can basically launch, for example, a configuration which describes a supercomputer or a cluster or even a particular pool of cloud resources. Each of those is given a config object. So all the configuration, which we used to do in XML and then JSON, is now done in Python objects. And you can sort of say, give me a set of nodes on this cluster. I want to run apps that are going to use 2 nodes apiece. I want these MPI parameters to be passed through to the apps. And you can kind of have that control. And you can be sitting in Jupyter kind of launching agents on these parallel resources and then type expressions. And, you know, workflows will kick off and run exactly as if you're sitting in a Python main program. So, yeah.
Cool. Please join me in thanking our speaker again.
Thank you very much.